Good afternoon. All right, this afternoon I'm not going to do 3 hours. I'm only going to do 2. All right, I'm a bit tired, so I'm going to show you. I'm going to start with solvent extraction, but I'm just going to do the calculation. All right, and I'm going to show you the 2 types of calculations that they may ask. So I'm going to do calculation for solvent extraction. Give me a second. All right, so I'll try to do those, as I said. I'm only going to do 2 hours. In the night, I might upload a video on a particular topic. All right, so that is what I'm going to do for the 2 hours. Actually, the first solvent extraction question, it's from, just a second.
So you need to go through the question that I put up on the YouTube page?
Please repeat.
Are you going to go through the question that I put on the YouTube page?
If I am going to do what?
If you're going to go through it.
Which question? These?
No, the one I put on the YouTube page.
Text me the question.
Spectroscopy, sir.
I'm not sure what you're asking.
There are the questions on mass spectroscopy.
Oh, yeah, I'm going to work it later and post it. Yeah.
Okay.
All right. Give me a second. All right, in solvent extraction, right? What happens? All right, so you will have two solvents, right? So for example, you have water, right? And you have a particular organic solvent, all right? So let's say ether, all right? Let us say you have a particular component, let's say iodine, right? In water. So what you're going to do, you have the two solvents, right? You shake it up, right? And you will see which of these two layers the iodine is more soluble in. So if iodine is soluble in ether, it will move up to this layer. Not all of it, but most of it. All right. So in solvent extraction, you have two solvents, and we basically want to see which of the two solvents the solute is more soluble in. All right. Basically, we'll have an equilibrium reaction between the two solvents. All right. That's the partition coefficient. So for this question, we basically want to see how the ester is distributed between the two layers. So when you're doing this type of calculation, it is going to be the concentration so this is the partition coefficient, right? If you want to find it, it is the concentration of your solute, right, in a particular layer. I'm going to say layer 1 divided by the concentration of the solute in, and the one at the top is always the more soluble one. So it's the concentration of the solute it's the concentration of this solute in the solvent that it is more soluble. You will not put this part in your equation, all right? I'm just explaining. So let us say iodine is more soluble in ether. It would be the concentration of iodine in ether at the top. And the solvent, which it is less soluble in, it will go below the line. So when you get the question, you will get two solvents. The one that the solute is more soluble in goes at the top, and the other one goes below it. So if we look at the question, right, it says a solution of 10 grams of an ester. So the solute here is ester in 100 cm cube of water. It was shaken with 200 cm cube of ether. After separation, the aqueous solution was found to contain 1.6 gram of Y. So remember, you have a solution of 10 gram of ester in 100 cm cube of water. So that means you would have started out with the ester in the water. All right. That means you would have added the ethanol to the separating funnel and shake it up. All right. And you added 200 cm cube of ether. So 200 cm cube of ether, and you have 100 cm cube of the water. When you start out with 10 grams of ester in 100 cm cube of the water. But afterwards, you found out that you don't have the 10 gram anymore. You only have 1.6 gram. So can anybody tell me where the others, the 8.4 gram would have went?
It would have went in the ether.
All right. So at the end of the process, you have 1.6 gram in the water and 8.4 gram in the ether. All right. So when we're going to do our calculation, this 10 gram here, it is not going to come into play. You have to remember how it is distributed. If I start out with 10, and at the end of the process, you have 1.6 remaining in the aqueous layer, that means the remainder has gone into the organic layer, which is the ether. The concentration that we are using is mass concentration. So for the ether, it is 8.4 gram in 200 cm cube. So we need to work out the ether. Right, so first, so the formula, it would have been the concentration of the ether, sorry, not the ether. It would have been the concentration of your ester, right, in the ether divided by the concentration of the ester in water. All right. So the concentration of the ester now in the ether. So let's do that part first. It would be 8.4 divided by 200. You don't have to convert to dm cube. All right. So this would be the ether layer. And for the aqueous layer, which is water, it would be 1.6 divided by 100. Let me see what was working out. Right, let me just double that quickly. So 8.4 divided by 200, you would get 0.042. So this is mass concentration. Unit is, well, it wouldn't be gram per dm cube. It would be gram per cm cube. And then 1.6 divided by 100, that would be 0.016. All right. So now we have the concentration. So we just plug it into the formula. So it would be,
Sir, if it's in grams per centimeter cube or dm cube.
just stick to one particular unit.
Okay, sir.
Yeah. We'll get 2.6. All right. I'm going to do it in dm cube over this side. So we see that the answer, it should be the same regardless. All right, so it would be, if we're working in dm cube, it would be 8.4 divided by 0.2 and 1.6 divided by 0.1. I think this will be 16. And so for this one, it would have been 42 divided by 16. You will still get 2.6. All right, so you can work in cm cube or dm cube. Also, the units, it would cancel. All right, so it wouldn't have any units. So if I want the partition coefficient, this is how you do it. You work out the concentration in each layer.
Hello, good morning,
Good morning.
afternoon. If you can hear me, I want to ask, so could you please summarize what you just showed? I just logged on.
It's a partition coefficient question for solvent extraction. So in this one, they tell you that you have 10 grams of an ester and you add it to 100 cm cube of water, all right? And you shake it with 200 grams of ether. They tell you that after separation, you have 1.6 grams of Y. To calculate the partition coefficient, it will be the concentration of your solute, which is the ester, in the two layers, the ether layer and the aqueous layer, which is water. How you know which one to put on top? You can do two things. ester is more soluble in the ether, so it goes on top. But if you read the question, you can get it from the question, because it told you that you put 10 gram in 100 cm cube of water, which means that is what you start out with. And then at the end of it, you're using the ether to extract it. So whatever you're using to do the extraction, you put it above it. All right, so whichever way you prefer it. Someone raised their hands a while ago. If you have a
Yes,
question.
sir. I have a question. How do you get the 0.2? So you have on the right hand side, you have 8.4
Oh.
over 0.2. How do you get that?
Oh, so for this one, we are working in DM cube. So let me put that. So over here, if you want to work in DM cube, over here, we just keep it in CM cube. So I was showing you that it doesn't matter if you keep it in CM cube or DM cube, the answer is going to be the same, 2.6. All right. So you don't have to waste any time and convert it to DM cube. Just work it in CM cube. Clear?
Wait, so like so when we have to put it in DM cube, we can just do it straight at the end and just say, you know, final answer divided by 1,000 or so.
No, the units will actually cancel. So you don't do any dividing.
Oh.
Yeah. So you can just work strictly in CM cube and you get the 2.6. Right.
Okay.
So this part over here, this calculation here in blue, this is working in CM cube. All right.
Also.
All right. So everything here is in CM cube. This is the
sir,
final answer. All right. So you can take a picture of the board. So they're going to do two things. Either they give you some information and ask you for K for the partition coefficient. And then there's a next way now I'm going to show you. Where was it?
Excuse me, sir. But where does, I know that I saw a little bit of the stream on YouTube, and I noticed that you started the funnel illustration and labeling, correct? So does the KPC calculations, they're the second thing you worked on?
No, I was just explaining the question.
Oh.
Yeah, so this, where they mentioned that it was shaken,
Yes.
everything will take place in a separating funnel. So you have the mixture of water and ester in the funnel, then you add the ether and shake it up.
I see. So the water is on the lower end,
right?
ester is higher end, and it's shaking up, and as a result,
all right. Last 30 seconds, let me just explain this. So when you're doing this, right, you have two solvents that are immiscible, like oil and water. All right. So the same thing here, ether and water, they are immiscible. So that is why I draw the line here. Then you're going to have a solute that have different solubilities in the two layers. All right. So the ester, it was in the aqueous layer, which is water. When you add the ether and shake it up, of the 10 gram, 8.4 gram of it move from the water up to the ether layer. All right. So for the partition coefficient, it's just a ratio of the concentration in the two layers. So it's the concentration in this layer over the concentration in this one.
Oh, I understand now, sir.
All right. Yeah. All right, so I'm going to do one from 2013. Let me find it. 2013. And then we move to our next topic. So I'm just going to do the calculation for this topic.
Excuse me, sir.
Yes.
Sir, do the questions get much more complicated from this? Like, is
All right.
there anything else, you know, to explain?
Yes, there's a next step. I'm going to show you now.
The
So they,
titrate.
so they're either going to ask for KP or for the mass. So I'm going to show you how to calculate the mass now. All right. So I'm going to clear the board. So if you're not finished, take a picture of it. All right, so I'm clearing it now. All right, so after all of this reading, what they want us to do is find the mass of the solid. All right. To get the mass of solid, you will need the partition coefficient. So if you look at the question, the partition coefficient, it was not given. So we need to find it. All right. So let's look at the question. It says when butane dioic acid was shaken with a mixture of water and ether, 10 cm cube of the water contained 0.854 gram of the acid, while a similar volume of the ether contained 0.159 gram. So what are they telling us? You have your separating funnel, you have the two layers. Down here you have the water, above it you have the ether, and the volume of each of them is 10 cm cube. All right. In the water layer, you have 0.854 grams. And in the ether layer, you have 0.159 gram. All right. So if you want the partition coefficient, you just work out the mass concentration. So I'm going to call this, all right, so I'm going to call it Y, all right, so to keep it simple. All right, so the concentration of Y in ether would be equal to 0.159 divided by 10, and that would give me 0.0159. The concentration of Y in water, that would be equal to 0.854 divided by 10. That would give me 0.0854. Oh, mass of acid, thank you. And so this should be acid, not solid. So now that we have the concentration of ether and water, let us see which one should go on top. So butane dioic acid, all right, so when this was shaken with a mixture of water and ether, 10 cm cube of the water contained 0.854, and the acid in the ether contained 0.159. Based on these numbers, the acid is more soluble in which one?
Water, sir.
Right. And so which one would we put on top?
0.854.
Right. So it would be the 0.0854 divided by 0.0159, and you should get 5.37. So the only mistake you can make here is putting the wrong thing at the top.
Excuse me, sir.
Yeah.
What did you say about how to determine which one is to go at the top again?
The one that is more the solvent that the solute is more soluble in.
So, sir, is this a case of what the bigger number, the higher
Right.
value number goes on top?
Wait, so when you look at the question, 0.854 gram of the acid dissolved in 10 cm cube of water, and only 0.159 dissolved in the ether. So this is telling us that it is more soluble in the water because a larger amount dissolved in the same volume. Understand?
Yes, sir.
Yeah.
So, sir, you didn't answer my question. So the amount that has the greater volume ratio is the one that's the numerator?
Yeah, because that would mean it is more soluble. So what was done to the right-hand side? All right, so remember in calculating KPC, it is the concentration that we are using. So in the question, it gave you the mass and the volume. So we have to calculate the mass concentration. So over here, we calculated the mass concentration. Gram divided by cm cube, gram per cm cube, that's mass concentration. All right, so your first thing I do is calculate KPC. All right, I'm going to erase the question now because we haven't actually answered the question as yet. So the first part of the question was to allow us to get KPC, the solubility. All right, so remember we said that this would be equal to the concentration of the acid. I'm just calling it Y, so I don't have to write out the entire word. So it is Y in water divided by Y in ether. All right. Now it says in a separate experiment. So let's look. In a separate experiment, 10 cm cube of water and 20 cm cube of ether were shaken together with 1 gram of the acid. So 10 cm cube water, 20 cm cube ether was shaken together with 1 gram of the acid. And they want us to calculate the mass of acid found in the aqueous layer. All right. So these are the two types of question. Either calculating KPC or mass. This is what you're going to do, right? So remember now, concentration is mass over volume. We don't know the exact mass of water because, the exact mass of the acid in water or the ether, because all they said they mix it with 1 gram. And remember, it would have been distributed, but we don't know how much in this particular experiment. All right. So for the mass of the water, so remember now we have KPC. So what you're going to do, right? For this calculation, we're going to use X to represent the mass of water. All right. So the mass of so X are the mass of the solute in the water. Let me say it properly. All right. The volume of water from the experiment is 10. All right. Look at the equation here. We have the concentration. This is the concentration divided by the the amount in the other layer. So you start out with 1 gram of the, let me use a different color. 1 gram of the solid. Based on how much goes in the water, it will decrease by that amount. So it is going to be 1 gram minus X. Remember, we don't know the exact mass, so we are using X to represent it. So it is X divided by 10, right? This part is working out concentration. Remember, this is mass, right? So mass over volume, that would be the mass concentration. So it's mass concentration divided by mass concentration. So X over 10 here, that is mass concentration. 1 minus X would be finding the mass remaining in the other layer. All right, so 1 minus X here, that is mass. And they are dividing it by volume, which is 10. All right, wait, not 10, 20. So for this calculation, right, you're going to start out with a lot of lines. So I'm just explaining it. Let's go back over here, right? When you want to find the partition coefficient, it's the concentration in a particular layer divided by the concentration in the next layer. Remember, concentration, remember, mass concentration is mass divided by volume. That is why you have X over 10, the possible mass in water over the volume, divided by, right, the possible mass in the ether over the volume. All right. So KPC would equal to all of this here.
Sir, there's something I don't quite understand. Why is it that for the 20 centimeter of a ether for that side, for the mass concentration, it was subtracted by 1, but for the mass concentration with the water at the numerator, it remains the same.
All right. So remember we said that we're using X to represent what? Quickly.
The mass of the concentration in the water. And
right. So if you have 1 gram, right, and you're using X to represent the amount in water. So let's say X was 0.5 gram. That means to get the amount in the other layer, you would have to subtract 0.5 grams, right? Yes, no, quickly.
Yes, sir.
Yes,
All
sir.
right. Yeah, so that is why you have X there. And that is why we have to subtract X here. So any amount that is in the water layer, you are subtracting it from the total mass. So that is why it is 1 minus X.
Oh, I
Yeah.
understand. So it's basically to equalize the amount of the unknown X amount in each liquid.
Right. All right, so let us make this a little simpler now. All right. So what I want you to do, right? Don't pay attention to KPC as yet. So what do we have here? We have X over 10, right? So I want you to do it like this. Or if you have a next way that is easier, no problem. All right. So you have X over 10. So X over 10, right? You have your division line. So x over 10 divided by 1 minus x divided by 20. All right. So just like with fraction, x over 10 times 20 divided by 1 minus x. Everybody clear at this point?
Yes, sir.
All right. So you can do two things at this point, right? 10 can go into 10 one times. 10 can go into 20 two times, right? So that would give you what? 2x divided by 1 minus x. Let me know if you're still following.
Yes, sir.
Following.
X. So look, 10 into 10 goes 1 times, 10 into 20 goes 2 times. So instead of saying 20x over 10 times 1 minus x, you just simplify these two numbers here. 10 into 10, 1, 10 into 20, 2 times. All right, let me just check if everybody is on the same page. All right. So this point, at this point now, remember KP is equal to all of this, right? But all of this has come down to what? 2x divided by 1 minus x, right? What was KP again? What did we get it to be? 5.37?
Yes, sir.
Right. So now, right. So now you can say 5.37 is equal to 2x over 1 minus x, right?
Yes, sir.
Let us cross multiply. So we're going to bring 2x on this side, all right? And we're going to bring 5.37 to this side. The 5.37, it is going to multiply the 1, and it is going to multiply the x. So you're going to get 5.37 times 1, 5.37. Take away 5.37 times x, 5.37x. All right. Once we reach here now, we're basically almost finished. We're going to bring over the 5.37 to this side. It was minus. When you carry it over the equal sign, we're going to add it. So it would be 2x plus 5.37x is equal to 5.37. All right. So now if you add up these, you would get 7.37x equal 5.37. So we are trying to find x. So we're going to divide both sides of the equation by this. So x would be equal to, let me see what I got, 0.73.
Sir,
Yeah,
I don't mean to slow down the process or anything,
yeah.
but like in the chat and stuff, and for myself too, a lot of us kind of got a little bit confused when the numbers started coming and the, so like if you could just, I forgot in depth all over again, but if you could just,
All right, let's do it again.
Yes, please. Thank
All
you.
right. So come back over to the left-hand side over here, right? All we're doing is dividing two sets of concentration, right? But it's just that we don't have a number for the concentration. So it's not like 0.5 over 0.8. Somebody's mic is on. All right. So x over 10, right? You just put that by itself, and the 1 minus x over 20, put that by itself. Because what we're doing is dividing all of this. You're dividing all of this by all of this, right? So it's x over 10 divided by 1 minus x over 20. So you just switch out this line here for the division sign. So remember,
why the minus in one again?
so this is the mass, right? And x is the mass of the solute in water. So if you want to know the mass in the ether, so remember the question work a while ago? You have 10 gram and 1.36 was in the water. So we subtract 1.36 from the 10 gram. Remember this question a while ago? And we got 8.34, right? So it's the same thing here. It would be like 10 gram minus 1.36.
Oh, okay.
Yeah, so X is the mass of the water, the mass of the solute in the water. But remember, we don't know what the mass of it is. That is why we are just using X to represent it. Understand?
Yes, sir. Thank you.
All right. So we're dividing X over 10 by 1 minus X over 20. So remember, a little fraction, if you have 1 over 4 divided by, let's say, 2 over 5, it becomes what? 1 over 4 times 5 over 2, right? Hope you remember that. Right, so that is why it's now x over 10 times 20 over 1 minus x. So we flip this side. So this changes to multiplication, and this part of it, you flip it. All right. So once you do that now, if these two have any numbers in common, you can simplify it. All right. So what I did, 10 can go into 10 one time, 10 can go into 20 two times. Then I just multiply the top. So 2 times x, that is 2x. So what I'm left with is 2x divided by 1 minus x. All right. Just bear in mind that Kp is on this side of the equal sign. So basically I was working out the right-hand side of our equal sign. So 2x over 1 minus x, that is the right-hand side of our equal sign. Kp is on the left-hand side. So the 5.37 now, I am introducing Kp. So 5.37, let me just put it over 1 if you want it as better. So 5.37 over 1 is the same thing as 5.37, right? So once you reach this part, you cross multiply. You bring 2x to the left-hand side, and you bring this over to the right-hand side. But you have to multiply it by whatever number is here, and you have to multiply it by x. So 5.37 times 1, I write it down, put back the minus sign, you times it by x again. All right, so that will be it. And then all you have to do now is carry all of this across the equal sign. But because it was negative, when it come across the equal sign, it becomes positive. All right. And then you just add them up. So 5.37 to 7.37. You want x. So whatever number is here in any future question, you divide it by 7.37. All right. And whatever you do to one side of an equation, you also have to do it to the next side. So we divide both sides by whatever number is over here. All right, so we have to move on again. It's 1 hour already. We are moving to polymers. So remember, this question was from 2013. The previous one was from 2012. In most cases, water would be below, but not all the time. All right? So you have to pay attention to the question. Let me say this, in the separating funnel, water is denser than your organic solvent. All right? Water is always below, but in your equation, that is not what we are looking at. All right? So just read the question carefully. All right? But as I told you, whichever is more soluble. All right, so we have to move on. This question is like 5 marks. So if calculation is a problem, you have 30 marks in module 3, 30 marks in module 1, you have chromatography, you have mass spec. All right. So don't let a 4 marks question throw you off. All right, guys, we have to move. So if you want to take a picture now, take it. I'm going to clear the screen. So basically doing polymerization. For each of the polymers, you must know their uses, all right? But I'm quickly going to go through the equations, how to get the polymers. All right, so the first one, we have 2 types of polymerization, as you know. We have addition and we have condensation. All right. So for addition, it's only alkenes. All right. For addition polymerization, it is only alkenes that will do it. And the 3 that are in the syllabus, polyethylene, polychloroethylene. This is also called PVC, which is polyvinyl chloride. So PVC, it's polychloroethylene, the same thing. And we must do polytetrafluoroethylene. All right, in these, the only thing that we're doing, right? Remember, polymers are large molecules. So we're joining up smaller alkene monomers. So the molecules that make up polymers, they are called monomers. All right. I'm going to start with polychloroethylene. The name of the polymer, it also, so for addition, polymerization, the name of the polymer, it tells you the monomer, because all we do is put poly in front of the name. So polychloroethylene, the monomer is chloroethene. All right. So to name the polymer, all we do is put poly in front of the monomer. All right. So let me draw a molecule now of chloroethene. We don't draw it like this. All right. Because we need to show the bond being broken and attached. All right, so all we are doing to make polychloroethene, we need to join up multiple molecules of chloroethene. All you need to do, this double bond here, we are going to break it. So let me just color code them, right? You're going to move one of these double bonds and use it to join these two compounds. So I'm going to move it from here.
Sir.
Yeah.
A third, a chlorine must be on the third monomer instead of hydrogen.
Yes. Thank you. All right. So all you're doing is moving the double bond and use it to connect the two monomers. All right. So we would move a next one from here and put it in front. All right. All right, so this is what we would have at the end of the process. We put the square brackets and the N to show that it can continue. So polymers, they are very large molecules. This is just showing a small representation of polychloroethene. All right, so there are many additional units, but I'm just using 3 to show it. All right, so we just put an N outside. So for this process here, I am going to write a question to represent what was just done.
Sir, why did you replace the single bonds between the two ones at the end with a plus sign, or to show the addition polymerization?
Which where? Down exactly where?
No, up here, so sir, why you put the plus sign?
Here?
Yeah.
Right, because we're joining this to this and this to this.
Oh, okay.
Yeah.
Sir, should you put back the other bond between the middle monomer?
Where? Which other bonds?
Middle one. Sir, the second one. Yeah, before the one.
Oh, yes, yes, yes. Thank you. All right, this polymer here, right? It has 3 repeating units. So if you look at the compound, right? Give me a second. Right, so if you look at this, what is repeating each time is your monomer, basically, right? 2 carbons with a chlorine on the first one. So these are your repeating units. So if the question asks you to do a representation with 3 repeating units, you will start out with 3 monomers. So if it had said 4 repeating units, then you would start out with 4 monomers. So each repeating unit is formed from a monomer. All right. So these are your monomers. Yeah.
Excuse me, sir.
Yeah.
The chlorine, it has to be on the first carbon, or can it be on top of the second carbon?
We put it on the first one.
Okay.
Yeah. But anyway, I take it like in this instance, it would appear like the first one. Yeah.
Okay, sir.
But the repeating unit, it will still look the same. Right? If you had started and put it in, if you had put it on this one, you would continue with that pattern for all of them. All right. So don't
Yes,
put
sir.
so don't put it on this one and then put it on the second one in the next one. Right,
Sir,
so,
do we need to know the structural formula for these?
Yes. So the repeating unit, it is Cl, carbon, carbon. It is basically a monomer without the double bond. All right, so that is my repeating unit for this one. So they could ask you to draw the structure of your repeating unit. This is it. No double bond is present. Put the 2 lines as well at the end of each carbon.
Sir, so if it asks us 3, sir, is 3 of that unit? 3 of that we would draw, sir?
No, just 1. So like if the question says draw the repeating unit, you just draw 1 of them. So this is polychlorate. So this is your polyvinyl chloride, right? Which is polychloroethylene. So this is PVC with 3 repeating units. If the question asks you to draw it, they just want to see 1 of them. So let me repeat what I'm doing here. This is the question over here. Write an equation to show the formation of polychloroethylene with 3 repeating units. And so I drew 3 monomers so that in my polymer, I would have 1, 2, 3 of them.
Sir, do we have to say on the exam, do we have to say polyvinyl chloride when they ask us what the name of the structural formula is, or is it okay for us to say polychloroethylene?
Yeah, man, it's just polychloroethylene because it's the polymer. All right. And we just put this out here to show that it continues. So this is just a partial structure. All right. All right, so again, just take a picture. We have to move on. All right, so this is chloroethene. Let's do polyethene. If the name of the polymer is polyethene, what is the name of the monomer?
Ethene.
Right. So all we're going to do is take off chlorine. All right. So we're using ethene now. So we're just removing the chlorine and put on hydrogen. So again, the process is the same. You just break the double bond and connect all of them, just like we have here. It's the same exact process. Once it's addition, you break your double bond and use it to connect the two carbons in front. All right. So the only difference between chloroethene and polychloroethene is the chlorine atom. All right. Nothing changes. So the repeating unit, again, all you do is take off the chlorine. All right. All right, so that's polyethene. All right, I'm going to clear the board now and we'll do polytetrafluoroethene.
Sir.
Yes.
Apologies. Did you write polyalkene at the bottom for the final formula?
Polyethene.
Oh, okay.
Yeah. So again, the process is the same. It's just what is on the carbons changes. All right, take a picture. If you're not finished, we're going to move to condensation now.
Sir, so what would be the repeating units?
All right, so to get a repeating unit, all you do, right? If when you look at the structure, hold on, give me a second. This right here, so this is your monomer, right? Give me a second. So for your alkenes, whatever monomer you have, you break the double bond, all right? Put one line in front of the carbon and one line behind of it. Everything else stays as is. And you will do that for any alkene monomer. This is how you get your repeating, your repeating unit.
Sorry,
Just,
tip code for me.
Okay, thank
Can
you.
just do that again, please? Say that
sure.
again, sorry.
All right, so quickly. This is your monomer, your repeating unit, you break the double bond. You put a line in front and a line behind of it, and that is it.
All right,
And
sir.
you, right, and you do this for chloroethene and ethene as well. All right. So if they ask you to draw, the polymer with 4 repeating units, it means that inside of it, you should have 4 of these. So this one I'm drawing here, it has 3 of them. All right. So let's move now to condensation. With this one, you will have 2 different monomers. In the syllabus, it says for terylene, you must use the exact structure. All right. And so what I'm going to use is that. So terylene, you will have a benzene ring with 2 carboxylic acids on both ends.
Sir, what about the removal of hydrochloride?
Yeah, in this, for this polymerization, it's
only water.
Right. So in condensation in general, it can be HCl. Right. But for condensation polymerization, we're going to join up these by removing a molecule of water.
All right, sir.
Right. So like with acyl chloride, right? That's when you get the HCl. All right, so you will have this. And the next monomer, it's ethane, and you have two OH groups on it. So terylene, it's a polyester. All right. So all we're going to do now, join up these two molecules. If you remember with ester, just look to the right. So you will have your carboxylic acid and you react it with your alcohol. And so all you're doing is removing the OH from the acid, remove the OH from the acid and the hydrogen from the alcohol. And so you will have C double bond O of the acid bonded to the oxygen of the alcohol. All right, and you put back everything else. So that is what I'm going to do here. I'm going to take away the OH of the acid. So the OH comes from the acid and the hydrogen from the alcohol. So I'm putting the plus sign because I am reacting this monomer with this one. When you're doing polymers, you see the group that is taking part in the reaction. So like for the benzene ring, it is the OH group of the carboxylic acid, right? So in my polymer, I am going to exclude the OH group. So it will start like that. The reason being, we are just drawing a small structure or a partial structure of the polymer. So we need to show that it can continue. And so you will have a free end here and your square bracket again. So C double bond O, this is gone, the H is gone. Next in line is the oxygen. All right, and again, hold on. This should have two OH. So when you look at this, right, it is the OH of the acid that is taking part. So at the end of my polymer, I do not put the OH. For the alcohol, it is the hydrogen that is taking part in the reaction. So that means I should have a free oxygen for the alcohol and the OH group, I take it off. I am going to add a next acid. So for this, the reaction is always between what? The carboxylic group and the OH group. So if I have a free OH group here, which molecule should come next? Is it the benzene ring or the alcohol again?
The benzene ring.
Right.
Benzene ring.
Because it's always the OH with the acid. So I'm going to do a next one. So again, hydrogen from the acid, from the alcohol, OH from the acid. So now this carbon, the H is gone, the OH is gone. Next in line is this group here. C. And I just draw back everything here. All right, I'm going to stop it here. All right. So this is a portion of terylene. All right, how many water molecules did we use to form this polymer? So one was lost here to form this. 3. All right. Let me highlight the third one. It would be this here. So you will get the polymer plus any amount of water that was used. So each time we join 2 monomers, we get a molecule of water. All right, so the next thing you have to do, right? After you draw your polymer, you have to be able to identify your repeating unit. Let me show you how to do that. All right, so the monomers, right? It was the benzene ring with 2 carboxylic acid. All right, so that means I am going to take off. So this is the monomer. When I'm doing my repeating unit, I am going to take off the OH. All right. So that is my repeating unit for the acid. But remember, it must be joined to the alcohol. So let me put the alcohol now. For the alcohol, the hydrogen is taking part. All right, so I take off the hydrogens. So this is the repeating, this is the structure, how it should look for the acid. This is how it should look for the alcohol. And remember now, the acid, it would have been connected to the alcohol. So this is the structure that I am looking for in my polymer. So all I need to do, right? If you want to start from the end, let me just erase this for a moment. So look, it must not have on the, start with your acid. It must not have on the OH on it. All right, so let's start from here. So this chucks the acid, right? And we know it should connect with the alcohol. And the alcohol ends with the oxygen. So you start from one acid molecule to the end of the alcohol molecule. So all of this is your repeating unit if you're asked to draw it. All right. So it's just the monomers connected together and the groups at the end that took part in the reaction, you will remove them. So you notice for the alcohol, it loses the H, and the acid, it loses the OH. So this is our repeating unit. So for condensation polymerization, you should know the repeating unit. The second thing you should know is to identify the bond. So in each of these, we have an ester bond.
So, sir, for
Yes.
unit are going to be basically the result of the acid and the alcohol reacting.
That is correct. Right. So it's the structure formed when the acid and the alcohol reacts. But just remember, do not put on any OH out here and any H at the end. So don't just connect them and forget to take off the H of the alcohol and the OH of the acid.
Sir, it's not,
Yes.
you don't add them because you leave them off because it continues basically.
That is correct, right? We have to, it's just a partial structure. So we need to show that it
Excuse me.
continues. Go ahead.
Could you repeat what she just said, please?
All right, so the reason why you don't see H here, so we don't put OH at the ends, all right? Because what we are drawing is just a small part of the polymer. So we want to show that it continues. So when it is continuing, right? This hydrogen, would this hydrogen be on the alcohol if we were adding a next acid?
No.
Right, exactly. That is why we don't include it. And if we're adding an next alcohol to this end of the acid, would the OH group still be there?
No, sir.
All right. So we leave off the OH and we leave off the H of the alcohol. All right. So for this, know your monomers. Know the actual structure of your monomer, know the repeating unit, and be prepared to draw a partial structure. All right, so we need to move again. So take a picture of the board if you need to. And we're going to move to nylon. Oh, let me give you the name of these. So the benzene one, it is benzene. So the name of the monomers, it is benzene 1,4-dicarboxylic acid. And the ethane, we call it ethane 1,2-diol. So if you see the names on the exam, you know which is which. All right. So these are your monomers for terylene. So once you say benzene 1,4-dicarboxylic acid and ethane 1,2-diol, you know it is terylene. All right, I'm going to clear the screen now. Could it also be called? Yes, it can be called benzene. Yes, benzene 1,4-dioic acid. And the only polymer with the benzene is terylene. So once you hear benzene in a polymer, it is terylene. The others don't have a benzene ring. All right, I'm clear now. So the next one now is, so we did polyester, we're doing polyamide. For polyamide, we're going to look at nylon 6,6. So this is a specific polyamide. And for this one, it is also a diacid. Diacid means 2 OH, 2 carboxylic group at either end. So the monomer diacid and diamine. The specific structure C double bond O OH so you must know the specific structure for nylon 6,6 and terylene. That is what it says in this syllabus. So this structure, right, it is actually 1, 2, 3, 4. So it is this. So instead of writing out all of this, we just group these, right? So these are 4 CH2 groups. That is why so we put CH2 bracket 4 because it's actually 6 carbons. But we have 4 CH2 groups. So instead of doing all of that, we need to save space. And so put CH2 in bracket and the 4 outside. So this is one monomer. The next one so again, we are going to join up these 2 compounds by removing a molecule of water. OH is always from the acid, hydrogen is always from the next compound. Remember, in my polymer, I am not going to include the OH. So it is C double bond O, CH2 4 dash C double bond O, NH, CH2 6. And I'm going to leave this end free. So this is a portion, but I'm just using the 2 monomers. I'm not adding any more to it, which means that this is us.
1 molecule of water here.
Please repeat.
You would just, at the end of this one, like the one before, you just said plus H2O, then no 3 or any number beside it, since you only removed water once.
Water should be there.
Yes, sir.
All right.
Sir, the
That
part
was
where
your.
the link,
Please repeat.
sir, the part where the link is that the amide linkage.
That is correct. Yes, so you should also be able to identify your linkage in this one. All right. So that's the amide bond. Same thing as saying linkage. All right.
So you would have N in front of the water?
No. Because this one, the water here, because we're showing a specific reaction between these 2, I can just put the 1 mole of water. So some textbook will put the N in front of it. But if CAPE asks you any amount of monomers you're using, put that amount of water.
Okay, sir.
All right.
Wow.
All right, so again, you're repeating unit. You would just take off the H of this, take off the OH of that, and connect the two. All right. So this is your repeating unit. The names of your compounds. So the diacid,
Sir, I'm confused about something. Didn't you already list out the monomers, the diacid and diamine?
oh
Why are
no,
you
that's
listing it again?
wait, no man. So diacid, right? Because it's 2-carboxylic acid, but the exact name of it is hexane dioic acid.
Oh, understood, sir.
Right. So just like with the ester, it would have been diacid and dialcohol, but you should know the specific name. All right. And this would be 1,6-diamino. All right, so I can take a picture. Let's move to protein. So we have to do protein now. All right, so I'm going to clear the screen on the protein. Yes, the linkage for terylene is ester bond, right? That is why I circled it. No, there's no mechanism for this one. We don't need to know any mechanism, just to write an equation to show the process. So we actually do 2 polyamides. Protein is one of them. So the nylon 6,6 is a polyamide. Protein is also a polyamide.
It's a natural and a synthetic, sir.
That is correct. So the protein is natural, nylon is synthetic. So for protein, the monomer is amino acid. All right. The general structure for your amino acid, it's a carbon, hydrogen, it has an R group. The R here represents the side chain. So it could be a hydrogen, it could be a methyl group, it could be CH2, CH3. All right. But we just use R. So it's the general structure. Next, it has a carboxylic group and it has an amine group. So unlike terylene, where you have to have your diacid and your diamine, the amino acid, it has a free NH2 group and a free COOH group. That means they can easily form polymers. So the NH2 group, we always align it with the COOH group. If you want to show that you're using 2 different amino acids for the R group, you just put R prime on it. So you put R on the first one and you put R prime. Again, we are always taking away OH from the acid, hydrogen from the amine or the alcohol. So the R group, it represents this high chain. So if I put R prime, I'm just showing you that the R groups are different. So R and R prime is to indicate two different amino acids. All right. So I just put a little dash on it to show that it's a different amino acid. Again, R represents this side chain or group of an amino acid. But for protein and the carbohydrate, you can use a generalized structure as well. So in the syllabus, the specific structure, it was for terylene and nylon 6,6. So we could also do this for protein as well. Let me just move this. So for protein, we could just have a box, all right? NH2 and the C double bond O, OH, all right? Because they said that the only one you need to use a specific structure for is terylene and nylon 6,6, all right? So you could do that as well. So instead of putting C, H, and R, you just put a box. All right, but here, if we are using specific amino acids, we would have N, H, again, this part is free. All right, there you have it, plus H2O.
Hello, excuse me, sir. The box in the equation writing represents the central carbon, correct?
That is correct.
Sir, what does it represent?
Please repeat. Oh,
I did not
so the
hear.
box. All right. Let me do it up here. So that is what it represents.
Sir, is it necessary?
No, you can, so the syllabus, you don't have to use the specific structure of the amino acid. So if you want to, you can use the specific structure of the amino acid, or you can use a simple box to represent the central carbon atom, this. So if you don't remember the structure of your amino acid, just know that OH, COOH should be at one end and NH2 should be at the other end. So you can use a box to represent this group, and then you just put COOH on one end and NH2 on the next end. So you can be specific as over here, or you can be general. So this is if you're being general about it. Over
And
here,
sorry, Sarah, you can only use this for the box for the protein because
we're using it because the syllabus said we can. All right. It said we can use the generalized structure. But for nylon 6,6 and terylene, they don't want the generalized structure. They want the specific one. So on the exam, unless they tell you that you can use the generalized structure for nylon, then you draw the benzene ring and put on the COOH groups on it. All right.
Sir, it's for the condensation reactions that we use the square brackets.
No, all of them. These are talking, right? These.
Yes, sir, because we use the circular or the rounded ones in the addition. So I was asking.
Oh, if you want to draw it like that, man, no problem.
N should be at the end of the bracket.
Please repeat. N, yes. Thanks. So if you prefer this structure on the right, no problem. Actually better too, but yeah. All right, so let me just complete this. So box C double bond O connected to NH, box C double bond O. All right. And again, this is our amide bond. No, because you can do it like this, you should still know the structure, right? Because if they ask you for it, you should be able to, you should be prepared to draw it. All right. All right. For carbohydrates, that's the final one. All right, so let's take a picture of the board. Let's move to carbohydrate, and we work to past paper and polymers quickly. All right, so I'm going to clear the screen now. So with this, right, the monomer is glucose. So again, with these, we don't have to use the specific structure. We can use our representative structure. All right. So glucose, you just have a box with two OH groups. But if you don't do bio, are we doing starch? It can be starch, cellulose, any of the polysaccharides. Now, if you go on the exam, right, and you see a structure like this, if you see something, anything like this, if you see any, once you see, if you don't do biology, right? And you see this box here, this is glucose. So if you once you see this, just know it's either starch, cellulose, any polysaccharide. All right. So if they gave you a representation and ask you to identify the polymer, right? So once you see any of these rings, the only polymer that does this is polysaccharides. So whether it's starch, cellulose, any other polysaccharide, right? So just look out for the glucose ring. So this is how glucose looks, right? Now, if they ask you to show it, you don't need to draw the ring. Just of the box with the two OH on either sides of it. All right. So all we need to do now.
I'm sorry, sir, but
Yes.
could you repeat that for the glucose, correct? From what I remember, don't we just combine them by aligning the fourth, so to speak, carbon number with the first?
1 and 4.
Yes, sir. 1 and 4 glycosidic bond.
Right. You have to be specific in bio, but for chemistry, you can just use the representation that I'm doing here.
Oh.
But I'm just saying, if they showed you a picture of it, for the persons that don't do biology, if you see a picture like this on it, right? So something like this, just know that you are looking at glucose. So it cannot be polyamide, it cannot be polyester. It will be a polysaccharide. All right. So once you see this ring, you're looking at glucose.
Right. By the way, sir, that box with the two hydroxides bonded to it, is that still representing an amino acid?
This here now?
The box, it's still representing amino acid, correct?
No, it's glucose.
Glucose.
Right. So we simply find the structure. Because if you know, in those reactions, it's two OH groups that are reacting. So we just need to draw a box with two OH groups on either side. All right. So again, now.
There's 6 would accept the box, right?
That is correct. So if you look in this syllabus at the objectives, and it tells us that for nylon and terylene specific, the other ones, it can be a generalized structure. So just go back at the polymer section and you will see where it says that. But even though it says that, still know the structure for your amino acid. All right. Because they can say bunting and do next. All right. So you take away OH from one and hydrogen, OH and hydrogen. So let's just join them up now. Oh, don't put on the H on it at the end. All right, so leave that.
Well, sir, seeing that for the first one, it was the OH that was being removed, then would the O still be on the box?
All right, if we match the pattern, if we take OH from this one, H from this one, OH from this, H from this, what would come from this one? Based on the pattern coming up.
OH should come off.
All right. So leave a free O here and just the bond on this part.
Yes, sir.
All right.
Sir,
Yes.
is that how we must represent the monomers for glucose with the
Right.
boxes?
Right. No, you don't have to state it for the person that texted. So for these, we don't need to do the complex structures. Let me just repeat that. All right. All right, let me get to a particle quickly on polymerization so you can at least, I'm just going to do the one asking about like doing the reaction. Let me see if I find it back quickly. All right, was it 2010? All right, I'm going to clear the screen.
Sir, I didn't get to take a picture, sir. Thank you. I'm taking. Thank you.
All right.
Right, sir. So that was for both starch and cellulose.
Right, because all of the two of them are polysaccharides, which means that glucose is what makes them up. All right, so for this question, we have a structure. All right, so this is on polymers. So this is compound A. I am at C number C2. All right, so this is C2. All right, so what type of polymerization would A most likely undergo?
Addition.
Right.
And why is that, sir?
Someone answer. Let me see.
Because of the double bond.
Right. So once it's an alkene, it's addition. Only alkenes do addition. So good job. All right. Suggest the repeating unit. All right. Part 4. Suggest the So what should I do to this structure to get the repeating unit. What did I tell you to do?
Break the double bond, sir.
Right. And then do what else? Right, so
Sorry,
Connect it to the same unit.
add the other monomers.
hold on. So all right, so just a second. So we have CH3, C double bond, CH3, CH3, and the H. So I am going to break this, right? And then do something else.
Add the line front and behind of it.
Right. One line in front, right? And that's it. So you just break the double bond, put a line in front and behind of it.
So you wouldn't bracket it in this case and put an N or something?
No, because it just asks for a repeat. So we are not joining a polymer now. So we just join the repeating unit. So it says suggest the repeating unit. If it had asked us to draw a partial structure now, all right, so even though it did not ask for it, let me do it quickly. So if they gave you this compound, right, and say draw a partial structure of the polymer that it would form, all right, containing 2 units. So this would have been 1 unit. And so then this now, we would do it again, right? Put a next CH3, the next CH3, CH3, H. All right, so if we're doing that, hold on there. So we only do the box thing if we are showing a portion of the polymer. Understand? But they did not ask for a portion of the polymer. They only asked for the repeating unit. So all you need to draw is this, and that, right? So this would be portion of polymer, and this would be the repeating unit. So here we go with the question. It says, right, the general structure of an amino acid. So as we said, the general structure, it has an R group, it has a hydrogen, a carboxyl group, and then amine group. So that's the general structure of your amino acid.
So what's the group that the N with the two hydrogen represents?
Amine.
Okay,
so NH2, it's amine. All right, I'm going to explain the reactions for the manufacturing of chlorine, the diaphragm cell. I'm going to explain the reactions occurring at the anode and the cathode. And then we calculate we do a little chromatography question, and then I'm going to wrap. In the night, I'll try to post a video with answering a few questions, but it won't be long. All right.
Excuse me, sir.
Yeah.
As it relates to macromolecules, it's
Mhm.
only structure we have to know. It's
No,
not
man.
like
No, you have to know the
uses as
uses.
all right,
Right.
thank
Yeah, man. So
you.
just check the study guide. They will have the uses. All right. So I was just doing the technical part. All right. Yeah.
All right, thanks, sir. Thank you.
Yeah, man. So like with chlorine, I'm just going to explain the reaction, but use the study guide to look for the uses and environmental impacts. All right. So I'm just going to explain the process. So I'm drawing the diagram from a 2018 past paper.
Sir, could you go back to that, please? So I can take a picture, please.
Sure.
Thank you.
All right.
So how fast does the video upload to YouTube after you finish streaming?
It's there.
Okay, so it just automatically stays.
Yeah. I'm going to add it to the playlist. So you can just click on the live playlist for unit 2. And you
Okay,
see
sir.
it. All right. So for polyethylene, in the study guide, look for high density HDL. You have high density and the low one. So make sure you know if you are looking for the uses, don't just look for uses of polyethylene, because they can answer about the high density or the low density polyethylene. All right. So when you're looking at the uses, study them separately. All right.
Sir,
Yeah.
I have some uses of them with me right now.
No, I won't be able to do it. All right. But I'm going to screenshot some and just post it on the community channel. All right. But I was just letting you know that when you're studying it, do the 2 of them. All right. All right. So 2018. Number 3.
So this is on chlorine, right?
Right. All right, so in the manufacturing of chlorine, right, we use sodium, we use concentrated, All right, this entire diagram is called what? Anybody know?
Electrolysis of brine.
Diaphragm cell. What's that?
Please
Or
repeat.
diaphragm cell.
Right.
Sir, is this the diaphragm cell?
Right. Diaphragm, right? So we use concentrated salt water, right? Which is sodium chloride. But you're also right, it is also called brine. So if you see brine, it is the same thing as sodium chloride. So they're asking us to label each of these parts, right? All right, so let me just tell you quickly. A reaction is going to take, as the person was suggesting, the process is electrolysis. So the process of electrolysis will occur. All right. Now, during electrolysis, a reaction will take place at the anode, and the reaction will take place at the cathode. All right. So before I answer the question, I'm just going to explain the reaction. All right. When you have a solution of sodium chloride, just switch ink. Just a second. When you have a solution of NaCl, you need to know the ions present. So you have sodium ion, as you would know, and you have chloride ion, right? But because it's a solution, you will have hydrogen ion as well as hydroxide ion. At the anode is the positive electrode that they are showing here. Which of these ions would migrate to the anode, positive or negative?
Negative, sir.
All right. So you would have the chloride ion and the hydroxide ion migrating to the anode. And at the cathode, you would have the sodium ion and the hydrogen ion. All right. So these are the ions present in the solution. Positive ones go to the anode. Sorry, negative ones go to the anode. Positive ones goes to the cathode. The next thing that you should be able to explain, right, is which one of these ions are going to take part. So is it the chlorine or the OH ion? And is it the hydrogen or the sodium ion? So at the anode, this charge here means that they are going to be oxidized to chlorine gas.
Could you repeat that, sir?
Yeah, I'm writing it in the bracket. All right, so in a concentrated solution of sodium chloride, there are much more chloride ions than hydroxide ion. So that is why chloride ion is going to be discharged at the anode. All right, so just remember that. For hydrogen, let me see if I can make it hold over here. All right, so hydrogen, it takes part because of its position in the electrochemical series, not because of the concentration. So for chloride ions, it's because of the concentration. For hydrogen ion, it's because of its position in the electrochemical series. All right, just take a picture for me. All right. I'm going to clear the right-hand side.
Sir, could you repeat the last thing I said?
No, I wrote, it is written here now. Hydrogen ions are discharged at the cathode because it is lower in the electrochemical series compared to sodium. All right, let me clear here. At the anode, so at the anode, let me do this. And so at the anode, what you will have is, let me put it underneath. The chloride ions are going to be oxidized to chlorine gas. All right, and at the cathode, the two hydrogen ions are needed to form hydrogen gas. Put a state symbols when you're writing equations. So two hydrogen ions will gain 2 electrons to give you H2. So you should know these two equations. That is what is occurring at the anode. This is what is occurring at the cathode. All right, so I think we can go ahead now. Yeah, question?
Yes, sir. If we had 2Cl and then had minus 2E, could that still work?
Yes, but the convention they use for CSEC is to put the electrons on the plus on the right hand side, but that would still work.
Okay, sir. Thank you.
Because it's showing the electron loss. So
Sir.
it's just go ahead.
Sorry, going off based if she had used the minus sign for the anode, like 2Cl minus the 2 electron. For the cathode, you would have to minus it on the right side for the hydrogen as well, just to show consistency. You'd have to use it for both.
Yes, I would say that, yeah. So if you work it right, so whichever convention you're working with, use it for the two of them. So if you're doing it like this, right, stick with this way. All right. If you do it her way, yeah, stick with it for both of them. All right.
Excuse me, sir. I have to ask, why is the for the anode and cathode, why is it that the chlorine and the hydroxide were placed as parts of the anode, while the sodium and hydrogen are placed as parts of the cathode?
Negative ions from electrolysis, negative ions migrate to the positive anode. Anode is positive, negative ions goes there. Cathode is negative, positive ions go there. All right, let us label this for me. All right, so if you look at the diagram, right, this part of it over here, this is the anode, right? So this is the outlet for a particular gas. Which reaction is occurring at the anode?
Sir, may you repeat the question, please?
Which
oxidation.
Right, and when chlorine is oxidized, what is produced at the anode?
Chlorine gas. Chlorine gas.
Chlorine gas, right. So coming out of this outlet here, so coming out here, that is chlorine gas. So I is chlorine gas. All right, so that's chlorine gas. What would be coming out at the cathode? Which gas?
Hydrogen gas.
Hydrogen gas. And we already know that this is the cathode, right?
Yes, sir.
Let me erase some of the writing off the board. All right, so this is the anode made of titanium. For the manufacturing, it's the diaphragm cell in this syllabus. All right. So it says you should know the diaphragm cell. All right, so the anode is made of titanium. Over here is steel. What else do we need to label? Oh, coming out of here, it would be sodium hydroxide.
Sir, may you
Give me a second. You will have sodium hydroxide coming out. All right. So I was just showing you the process, right, and the reactions. Now, if you look at the objectives of this syllabus, all right, you will need to know the benefits of the diaphragm cell compared to mercury, uses of the halogens, and so forth. All right, those, just read it. It's in the study guide, shortened, right? So just look at your syllabus and look at what it says you need to know and just get it from the study guide. This is just the technical aspect. You just need to know which reaction is occurring at the anode and the cathode and be able to write the equation. Tell why chloride ions take part as well as hydrogen. And you should be able to draw and label your cell. All right. So that's what I'm covering for this. All right. So in terms of the past paper, it had asked us to label it, right? And then it asked us to write equations. Let me just put the question or just the answer. So this here, it would be for A part 2. So this over here, this would be the answer for A part 2. So for A part 1, we labeled it. A part 2, it asks for the equations for the reaction occurring at the anode and the cathode. All right, I'm going to do cracking. All right, so V can be, yes, it's a mixture. So just put a slash here or comma. Mixture of NaOH and NaCl. All right, again, take a picture. Go ahead.
Sir, I saw one of the participants was asking what was the use of the diaphragm?
I'm going, hold on. I'm not hearing you clearly.
So it was asking if the diagram had like cracking in it or something like that, what would happen?
You can text it. If it have acid in it.
She said cracking, sir.
Please repeat. If it crack. Oh, cracking. As in the topic cracking of alkane? I didn't hear
No,
you.
sir, she's asking if the diaphragm has cracking in it, what would happen?
Oh, I was going to answer that after because I want to move on, but I'm going to post it. But you see, this is to separate the two components, right? So if it has crack, they are going to mix. The two components are no longer separated. All right. I'm going to post the picture of that answer. All right, but the two components, they will no longer be separated. All right, but we have to move now again. All right, so cracking, I'm just going to remind you of the actual process. All right, just the equation. All right, so let me clear the board. Take this one. Clear this. All right, cracking. So you have your all right. What are the two types of cracking? Quickly.
Thermal and catalytic.
All right. All right. So we have thermal cracking and catalytic cracking. What are the catalysts?
Alumina and silica.
Right. So we can use SiO2 or Al2O3. For the thermal cracking, what was it again? Was it 700 to 900?
Yes, sir.
Yes, sir.
And this was 400 to 500? We can double check. I think it's 400 to 500.
Yes, sir.
All right. So I'm just going to do an equation, all right? So we only crack alkanes, right? So cracking, what happens in cracking? We're basically converting what?
Alkenes into alkenes and smaller alkenes.
Right, so we're converting large alkanes into smaller alkanes and alkene. All right, so for example, let us say you have C8, H18, that would be the alkane, right? And let's say we're doing thermal, so 700 to 900 degrees Celsius. When you crack it, right, the exam, they can tell you, if they ask you just to show the process, all you need to show is two products, right? So we know one must be an alkane, one must be an alkene. If you have 8 carbons and we want 2 fragments, just somebody, how much carbons do you want in the first fragment?
4.
All right. So if the first one has 4, the second one must have 4. One must be alkane, one must be alkene. So if this is the alkane, how many hydrogens should it have?
8.
8. All right. Wait, this would be alkene if it has 8. If this is the alkane, how much should it have?
10, sir.
Right. Let us do it again, but this time I want 3 products. So choose again. How many carbons do you want in the first fragment?
So the second one is the alkane, right?
Oh, yes, thank you.
So say you'd have 2 alkenes and an alkane, or 2 alkenes and an alkene.
Okay, second I go to that, like the things we need to know. I did benzene in the other class already. I can't do it again. I probably can just do one reaction. All right, if I want 3 products, right? How much carbons do you want to be in the first one?
2.
2, all right. How much you want in the second one?
3.
All right, 3 and 2, 5. All right. So remember, anything on the right-hand side, it should add up back to the left-hand side, right? So the first one, do you want it to be alkene or alkane?
It can be an alkene.
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 Whichever one. So you choose. All right. So if you want it to be alkene, it would be H4.
H4.
What do you want to make this one? All right. Let's make it an alkene first.
Alkene.
All right. So let's start out with alkene and alkane, right? If we do that, how many hydrogens have we used
12.
up? 12.
12.
Right. That
Another
means how much we
alkene.
have leave?
Another
6.
alkene. 6.
Right.
Another alkene.
So once you crack an alkane, to get 3 products, 2 of them must be alkene. All right. So once it's 3 products, it must be you must get 2 alkene. So ethene, propane, and propene. All right, so just know to do the equation for cracking. Again, for this, you have to know the fractions. All right, so ensure you're looking at your objectives and you can just, for module 3, you can just use this study guide. All right.
Sir, the examples you gave are thermal cracking.
It doesn't, no, it's just the condition, you know, so you would still get the products.
Sir, pardon me, sir, I'm back. So I know ethene is the alkene and propane is the alkane. So what way can we like remember what's an alkane apart from looking at it from a structural point of view, like if it's just a name, like just letters and numbers and no branches connected to it? How can we be able to remember or discern which is an alkene and an alkane?
General formula of alkane is CnH2n plus 2. Alkene is CnH2n. So this is alkene. That one is alkane. N is the amount of carbon. So quickly, if you have a carbon with 4, if you have a compound with 4 carbon, for it to be an alkane, it would be 2 times 4 plus 2. So it would have to have 10 hydrogens. Is that what you're asking? Not sure.
I was just trying to figure out like how I could discern between the two based on the numbers. So what you're saying is like if it has like a 4, if it has 4 and 8 here, 8.
All right. So for the alkene, it has twice the amount of hydrogen as carbons. C3H6, C2H4, C5H10. That's how you know your alkene. It's always has twice the amount of hydrogen as carbon. Clear?
Yes, thank you, sir.
All right. The alkane it has twice the amount of hydrogen plus 2. So C3H8, C2H6, twice the amount plus 2 more. All right, that's that. All right,
Yes,
clear
thank you,
this.
sir.
Yeah, man. Clear this. Before I end, I'm going to do some module 1, just some general reactions to jog your memory. All right. So take a picture of the board. So for the next 12 minutes, we're just going to do some reactions in module 1. All right, I'm going to clear the board now. All right, so first, how do you differentiate between alkane and alkene?
Alkenes have a double bond.
No, in terms of test.
Well, alkenes will decolorize potassium permanganate, right? Or something?
The bromine test.
Right.
With
Bromine.
bromine water. Alkenes decolors bromine water, I believe.
Correct. All right, so so you can use KMnO4, or you can use bromine water. Tell me your observations quickly.
The potassium changed from purple to colorless.
All right, purple to.
And then the bromine depolarized.
All right. So you can put purple to colorless, or you can say it will
Pale
be
pink.
No, it will decolorize. If you use acidified, it will go to colorless if you acidify it. So if you want to say purple to colorless, or it is decolorized, you can say that. And for the bromine water, it will go from, wait, let's.
Red to colorless.
That's a
Or
second.
white.
So for the alkene, let us specify it. So the alkene will change it from purple to colorless. All right. For your observation for alkane, put no visible reaction, or you put that the KMnO4 remains purple. So the observation for alkene, purple to colorless, or it is decolorized. For the alkene, no visible reaction, or you say it remains purple. Yes, whether it's liquid or aqueous, bromine. All right.
Sorry, you forgot the chromatography questions.
I'm going to work one with the retention factor shortly. All right, so that's with bromine. All right, orange to colorless. All right. For this one, specify in the absence of UV light. So for bromine, specify in the absence of UV light. So you must mention that.
Excuse me, sir.
Yes, go ahead.
I thought bromine is red or brick red or something.
The bromine water, it has an orange color.
Oh, okay, thank you.
Yeah. Also, if it was the liquid one, then you would use that color. But the bromine water, it has an orange color. And so in the absence of UV light, because remember, alkanes react with halogens if UV light is present. All right, so take a picture.
Alkanes,
Please repeat.
You said alkanes.
No, alkanes. So for bromine, the alkane reacts with it in the presence of UV light. So in the presence of UV light, both the alkane and the alkene will decolorize it.
So this is for both alkene and alkene.
All right, let me clarify. So alkanes, no reaction with UV light, sorry, no reaction with Br2 unless UV light all right. If present, Br2 is decolorized. Clear? So if you are distinguishing between alkane and alkene using bromine water, UV light cannot be present. All right, take a picture of the board. I'm going to clear the screen.
Sir?
Yes.
Is this primary, secondary, and tertiary alcohols?
Yes, I want you to identify them as primary, secondary, or tertiary.
Right now?
Yeah.
Well, the first one is primary.
First one is primary.
The second one is primary as well.
All right, if you get the go ahead. The second one,
Isn't it primary as well, sir?
I know why you say primary, but it's not. If you get the condensed formula, it's best to draw the.
Is it a secondary?
Not secondary either.
But sir, isn't it something there? Isn't it a methyl group attached to the carbon with the
Oh, sorry.
hydrogen?
Wait.
That's
Yeah,
what I'm
so
saying.
I was saying.
No. Check it now. Yeah, I forgot
Yeah,
to.
no, it's tertiary.
No, it's
Right.
tertiary.
Tertiary, sir.
All right, so once it's at the end of the chain, it's primary. Just to note that this one is not at this one here. Let's draw the structure, right? So we have a carbon with 3 methyl groups. So if you are present and you're not sure how to determine if the OH group, if the alcohol is primary, secondary, or tertiary, I'll just quickly show you. So what you're going to do, you're going to pay attention to this carbon, the one that is bonded to the OH group. All right. When you look at it, if 3 carbons are directly touching it, it is tertiary. So 3 carbon atoms directly attached, it is tertiary. All right. So you can see 1, 2, 3 directly touching it. All right. If 2 carbon atoms are attached, it is secondary. Like you can see here, if you draw it out, right? CH3, CH2, CH, OH, CH3. This carbon atom is connected to it. This one is connected to it. So 2 carbon atoms, it is secondary. And 1 carbon atom, it is tertiary. Sorry, primary. If you prefer to use hydrogens, you can do so. If 2 hydrogens are attached, it is primary. 1 hydrogen, secondary. No hydrogen, it is tertiary. So you can use hydrogens or carbon. So if you look at this one, no hydrogen is attached, so it is tertiary. This one, 1 hydrogen is attached, so it is secondary. And this one up here, 2 hydrogens are attached, so it is primary. So you can choose which one you want to choose. Question. Right. What will be the color change if you add potassium dichromate to 1,2,3? Let me put it on the board quickly.
Okay, so 1 and 3 is purple to colorless, and 2 would not react.
Right.
Yeah.
Sir, tertiary usually don't have any reactions, correct?
That is correct.
It's
All right,
similar,
so
similar to ketones, right? There's no like reaction.
except ketone.
Well,
Which
ketone
compound
has
can
one.
ketone? Which
The
compound
D,
ketone can react with?
is it the DNPH or
Right. And what's that
Talent
also called?
reagent, or Brady's.
Right.
pardon, sir,
And
can you
talent
get,
reagent,
No, it
or
don't
no,
react
no,
with talents.
oh yeah, it
it
doesn't.
only Brady.
And
Right, I'm going to get to it in 2 minutes. So let's just quickly answer this. All right, so when we add KMNO4, compound 1, so 1, it will decolorize it, right? 2, no visible reaction, right? Because tertiary alcohols are not oxidized by KMNO4.
Excuse me, sir.
Yes.
I just want to ask before I forget. So sorry if I'm skipping ahead, but
Please repeat.
I'm just asking. Phenols do not react with produce a positive result for KMNO4, correct?
Right. So right. So benzene ring, it don't react like your regular alkene.
Alcohol. All right.
Yeah. It will
Thanks.
react with bromine, however, if you use FeBr3.
Oh yes. Yeah.
All
Thank
right.
you, sir.
Sure. All right. And for this one, again, it will also decolorize it. All right. My next question. All right, so when compound 1 reacts with the potassium permanganate, which functional group will you get?
Aldehydes and then carboxylic acids.
Right. So compound 1, it will give you carboxylic acid. What will compound 2 give you?
A ketone.
Nothing.
No, it will
Nothing.
remain as alcohol, right? So remember, compound 2 is a tertiary alcohol, and tertiary alcohols are not
Don't react.
oxidized.
Not react.
Right. So it will remain as alcohol. And the third one, what would we get?
Ketone.
Ketone. That is correct.
So sir, you can write RXN on paper tomorrow? Like
No.
as a shorthand?
Write out the word.
All right.
So primary alcohols give carboxylic acid. Secondary alcohols give ketone. All right. Question. All right, let me put it up top. How would you differentiate between compound 1 and 3? No, compounds 1 and 2.
I had a farm test.
Compounds 1 and 2. All right, I was saving that one for compounds 1 and 3. So if you remember, compound 2 is a tertiary alcohol, right? And tertiary alcohols are not oxidized. All right, so you could use KMNO4, K2CR2O7, or iodine in sodium hydroxide, which is the iodoform test, to differentiate between primary and tertiary or secondary and tertiary alcohols. Wait, you wouldn't use iodoform for secondary and tertiary though? Because remember, secondary and tertiary can do the iodoform test. All right. So if you want to differentiate between primary and tertiary, you can use potassium permanganate or potassium dichromate. All right. So, all right, so let me just take off this part. So all of these three can differentiate between primary and tertiary.
Wait, so you said that tertiary alcohols undergo the
Iodoform test, yeah.
You sure?
Yep. A primary alcohol.
Only primary. So
remember, primary alcohols don't do iodoform. You need a methyl group, and tertiary alcohols have that. All right, ethanol is the only primary alcohol that does the iodoform. Reaction. All right. I want to stop there for alcohol. Quickly erase the word aldehydes and ketones. What do they have in common? Aldehydes and ketones. Which reaction?
A carbon. Oh, which reaction?
Which reaction aldehydes and ketones have in common?
With hydrogen cyanide.
Yes, but in terms of test,
The test of carbonized.
The Brady's reagent.
Right.
With the 2,4-D and pH.
That is correct. Right. 2,4 DNPH, and that is called what? Brady's reagent. What color change are we looking for? And anybody remember?
Orange.
Right. So we're for a bright color, right? So we're looking for an orange precipitate. Test to distinguish them now. Which test can we use to distinguish between aldehyde and ketone?
The tolerance reagent.
Yes. What else?
Silverman.
Reagent.
Whose reagent?
Silverman test.
Early.
Right. All right, so we can use Tollens, which is the silver mirror test.
Use potassium for them.
Which one did it say again? You had said Phalins. And which other one? KMNO4 as well. Remember, aldehydes are easily oxidized. You can use K2CR2O7 as well. Remember, ketones will not react with any of these. In terms of observation, from blue to brick red, we know that this will be decolorized. This goes from orange to green. Right. For the tollens, we get a silver mirror as it says, or if you want to put silver precipitate.
Sir, did you
Yes.
say the ketones or aldehydes were easily oxidized? Which one?
Please repeat.
Sir, which one of them did you say were easily oxidized? Was it ketones or aldehydes?
No, aldehyde. So you see, all of these are reactions of aldehydes, not ketone.
Okay, sir.
Right, so all of these are to distinguish aldehydes from ketone. And in each of them, the aldehyde is going to be oxidized to a carboxylic acid. Right, I'm going to do a reaction scheme with benzene, a calculation with chromatography, and then I'm going to end it there.
Wait, sir. So what you're saying is the test that both aldehyde and ketone have in common is the Brady's reagent test.
That is correct.
Oh, is it all right if I just write that on the exam, or do I have to say the 2,4-D and pH?
No, you can put Brady's reagent.
Okay, sir.
By the way, when you oxidize primary alcohol, what we get again? Aldehyde, right? If you use a weak oxidizing agent, you will get the aldehyde. If you oxidize ketone, which alcohol you get?
If you oxidize ketone?
Second.
Right.
Sir, would it reduce?
Wait. If you oxidize secondary alcohol, you will get
ketone.
All right. If you reduce a ketone, what will you get?
A secondary alcohol.
And if you reduce aldehyde, what will you get?
Primary alcohol.
Primary
What will you
alcohol.
use to reduce the aldehyde?
Stop. Reduce so LiALH4 in dried ether.
Right.
Or NaBH4 in aqueous alcoholic solution.
Right. But we use LiALH4 is in this syllabus. All right. What is the color change? All right.
I don't remember. Orange to red.
Yes, you get a bright precipitate. Hold on. Let me just undo this. All right, lithium aluminum tetrahydride, it reduces aldehydes to primary alcohol. It reduces ketone to secondary alcohol. Right, I'm going to erase the left-hand side of the board. Everybody did have it, right? Did everybody take a picture of the board? Just check in quickly.
Yes, sir.
Yes, sir.
All right. All right. How do I go from that? I want you to tell me reagents and conditions if conditions are needed. So how do I go from this to this? Tell me, which reagent?
Concentrated nitric acid and concentrated sulfuric acid.
All right, concentrated nitric acid, concentrated sulfuric acid. Any condition?
Yes, sir. From 50 to 60
Excuse me, sir.
All right. And what is the name of this process or this reaction?
Nitration.
Nitration of benzene.
That is correct. Give me a second. All right, how do you go from that to this?
Reduction.
Which reagent?
Zinc and concentrated HCl.
All right, tin
or zinc.
and HCl. All right. What is the name of this reaction?
Reduction of nitrobenzene.
All right, reduction. Now, if I go from that
to state the condition.
this one, yeah,
None.
Yeah, this one don't need any. Hold on, that's a little too far up. Okay. How do I go from this to this?
They use HCl and HNO2.
All right, nitrous acid and HCl. Any temperature?
0 to 5 degrees.
All right, so HNO3, no, not HNO3, HNO2 and HCl. The condition, it very like in some book, you will see below 5, others you see below 10. All right. That would be great. So this is just done. All right. Who can tell me what would come next? Or take a guess which compound I'm going to do next.
A dye.
Right, correct. Right. So this is a familiar scheme that they love to send. All right. All right, so my question then is, which compound would I react it with to give me the dye?
Phenol.
Right. Oh, by the way, what is the name of this reaction from the phenylamine to this compound?
Diazetaization.
Right, so this reaction
Could you
here,
repeat what was it a while ago, sir?
I was asking for the name of the reaction from the phenylamine to, what is this, what is the general term for this compound here?
Diazonium salt.
Right, so we get a diazonium salt, and the reaction is called diazetaization. And they said we would react it with phenol, right, which is this. And we're going to get a di. So in time we're doing the di, we're going to turn it sideways. All right.
Why is that turn sideways, sir?
I don't have to, but it's kind of convenient. You just put this. Also, for the di, you're going to, the nitrogen triple bond, it just basically you take off the chlorine off of it, remove one of the bonds. So the nitrogen triple bonds, it becomes nitrogen double bond. And the nitrogen, you're going to connect it to carbon 4 of phenol. All right, so if you align phenol in this manner, it goes here. Otherwise, it would be one on top of the next. All right, so this is your azo di. Or if you want to say azo compound. All right. So now this reaction scheme. Please repeat.
There's no temperature for the reduction of nitrogen.
If there's no condition, no, just room temperature. So there's no extra cold or warmness for it here. All right, so let's take a picture. Let me clear again, because I want to wrap now. Do you remember the reactions of phenol? If phenol react with bromine, tell me 3 observations. All right, before you answer, sorry, before you answer, ensure you have the picture. I'm going to clear the screen. All right, go ahead now.
Why precipitate?
Antiseptic smell.
Right, and one
And
more.
bromine is decolorized.
That is correct. So if we wrap phenol with Br2, what is the name of the compound that we are going to get?
2,4,6 tribromophene.
Wonderful. So phenol is still there. We're going to get 2, 4, 6. As I said, in terms of observation, you get the white PPT. And what else did we say, right? BR2.
Aseptic smell.
Right, and BR2.
Decolorized.
Right. You can react it with an acid chloride, ethanol chloride, so CH3, C double bond O, Cl. You're going to take a, let me see this. Okay. For this one, it's condensation that they were referring to. when I was doing condensation polymerization. So for this, we are going to get HCl. So you're going to take off chlorine, take off the hydrogen. This carbon with the double bond O will attach to this oxygen. So let us do that. All right, so O, so I'm going to switch, I'm going to flip it around, right? So C double bond O, CH3, all right? And remember, if you react it with sodium hydroxide, you will get this O, Na. All right, that is with sodium hydroxide or sodium metal. All right, take a picture of that. Let's look at calculating retention factor for chromatography. All right, so I'm going to clear the screen. Where you said that is the last thing I draw. Oh, all right. Let me just do it properly. So for this one, all right, let me just do it good. So if you react phenol with sodium hydroxide or sodium metal, you will get the same product, which is the major product, that is, you will get O and A. All right, that. What were you talking? Oh, I was saying that if you react, this is an acyl chloride, ethanol chloride. When you react it with phenol, you're going to take off the chlorine, take off the hydrogen. This carbon here, you're going to attach it to the oxygen. So if you notice, the carbon with the double bond oxygen, it is bonded to the oxygen of phenol. All right, so let's just do that calculation quickly. Right there. All right, so chromatography, as you know, we do it if you want to separate a mixture of dyes. Give me a second. No, I was saying that this reaction is still condensation because we are joining up two compounds by removing a molecule. So we are not removing water, but it is still condensation. So we join up these two, so you will also get HCl as a product. So it is condensation. It is not condensation polymerization, but it is a condensation reaction. All right, I'm clear now.
Yes, sir.
All right. I'm just going to look at the technique, all right? Well, not the technique. So you should look at thin layer, paper, column, and gas. All right, I'm just going to do the calculation for thin layer, which would be the same thing like paper. All right, so this represents your chromatogram, right? Let me draw it taller. All right, let me just do the past paper one. Give me a second. I'm not sure which year this one is, but I'm going to do it. All right. This line here, it's called the solvent, it's called the origin. So if you get anything to label like this, you will have a line built at the bottom and one at the top. This one is called their solvent front. This is the origin, all right? And this is where you would place your sample of dye. Your solvent, it would travel up the paper, right? And separate it. So this is from a past paper. I'm going to put the measurements now. So this is all right. So to get the what we're going to calculate now. All right, let me put the question. Calculate the RF values. Calculate the RF, and RF stands for retention factor. So to do this, RF, it's the distance traveled by the component divided by the distance traveled by the solvent front. All right. So for A traveled a distance of 2.4 centimeter, and the solvent front, which is Z. So the solvent front is the distance from the origin to where we stop it. All right, up here. Yes, this is the last thing. All right, so 2.4 divided by 6.8. And B would be 5.1 divided by 6.8. Anybody work it out? All right, let me.
B is 0.75.
Thanks. So B is 0.75. It has no units, of course. And then A is?
0.35.
All right. All right, I'm going to answer a part for you, so you'll get this. Last part now, it says, well, the last part, I am going to work, explain, no, suggest. All right, so let me tell you what happened now. Why this one did not move as far as this one. Take a picture of the board. I'm going to just clear off some of this. And so take a picture of the board. All right, so remember now, this is a filter paper, right? Or if it was the thin layer. All right, hold on. So this would have been in a container, right? With your solvent, which must always be below the line of the origin. Now this solvent, it is going to travel up the filter paper, right? Now, as it travels up the filter paper, the components in your dye, they will have an attraction for the paper as well as for the solvent. But they will have different attraction for the paper and the solvent. If the one that moves farthest, and by the way, the solvent, this is your mobile phase. So your mobile phase is the liquid, in this case, that moves along the stationary phase. So the paper, all right? So if B travels farther up the paper, right, it means that it is more attracted to the right. So it is just moving more freely with the solvent, which means that A is more attracted to the filter paper. All right. So for one, I'm going to say B is more attracted to the solvent and A is more attracted. Or we can say B is more attracted to the mobile phase and A is more attracted to the stationary phase. Now, if they are attracted, it means that they have to have something in common in terms of their polarity. So remember, when we did solvent extraction earlier, if it is, water is polar. If the solute you put in the separating funnel, if it is polar as well, most of it will be in the water, right? Instead of the non-polar layer. So with this one, if B is moving with the mobile phase, it means that its polarity is similar to the mobile phase. And if A is sticking more to the stationary phase, that means its polarity is more similar to the stationary phase. So it is more attracted to it. So the more similar the more similar their polarity is, the more they stick to each other. So when you hear the term like, dissolve, like, it's basically mean they have the same polarity. All right, so my two reasons, I'm going to put it now. So one, B is more attracted to the mobile phase. Give me a second. All right, so B is more attracted to the mobile phase, and A is more attracted to the stationary phase. Secondly, B has groups with similar polarity. All right, so that is, so for any form of chromatography, that is the principle on which we basically separate them. The affinity of the components for the mobile phase and the stationary phase. So that is basically the principle. Each component will have a different affinity for the mobile phase versus the stationary phase. So anyone that has a higher affinity for the mobile phase will move with the mobile phase more freely. All right. So I'm going to end it here. All right. So all the best tomorrow, and just see what you can do with your studies and practice. All right. So I'm going to end it here. You can take a picture of the board.
Thank you, sir.
Yeah, I will do the mass spectrum question that I promised to do later and post it.
Thank you, sir.
You're welcome.
Thank you, sir.
All right.
Thank you, sir.
Yeah, man.
Thank you.
Appreciate it, sir.
All right.
God bless you.
Thank you. All right, so I'm going to stop. I'm going to stop sharing now.